Let's talk just a little bit about forces and types of forces that we need to be aware of when we start to try to understand human movement. All right, let's start with the definition of a force. It's a push or pull that tends to cause movement. It doesn't have to cause movement. I can push on the table. I don't have to move the table, but we're going to be interested in when forces start to cause movement. Now, there's different ways to categorize forces, and sometimes it's helpful to do that. So I'm going to put forces into two categories. So I'm going to say types of forces. And the first category I'm going to say is contact forces. And where there's a number of forces that in this category that we need to spend some time on. Friction force. This is the interaction between two objects or two surfaces that are sliding against each other or maybe not sliding. Then we have ground reaction force. This is the force of the ground pushing on the object. And when we start doing human movements, we'll have people do movements on a force platform, and then the ground reaction force is a reaction to what the person is doing. Person is pushing on the force platform, and Newton's third law tells us there's an equal and opposite force pushing back on the person, and that's the ground reaction force. Drag force is an important force that we're going to spend time on. This is the force of a fluid pushing on an object, and this fluid could be air, so we call it air drag force, or water, so we call it hydro drag force or water drag force, so hydrodynamics. And it seems weird to put that into a contact force, but these are air and water particles pushing on the object, and so there's a contact between the fluid and the object, so that's why it's in the contact force. Then we may get a little bit to this one, but it's a spring force. And this is an elastic force. So if we stretch something, it wants to pull back. That creates a force. Or if we compress a spring, it wants to spring back. And this becomes important in the context of this course in looking at things like shoes that may compress while running, or maybe even biking, where the tire may compress and then recoil. That becomes an important force to understand. And then finally, applied force is anything that I'm not considering here. And it's anything external to the person. Again, we're dealing with human movement. So someone pushing on somebody else, or some object contacting a person, something like that, or sitting on a bike. There's some other contact forces that we need to deal with when biking. All right, so those are contact forces where two objects are in contact with each other. And I'm going to go through these forces in detail throughout the semester. The other category, seems obvious now, is going to be non-contact. And the main non-contact force that we're going to be talking about is gravity. Gravity is a force pulling on the person or on the object. That is an interaction between the two objects, but they're not touching each other. Some other non-contact forces would be electrical force or magnetic force. I don't think we'll get to those types of forces, so I'm not going to list that here. But those would be other examples of contact force. Obviously, magnets can pull on each other or pull on metal pieces or different things like that. So it is a force, and it's a non-contact force. Okay, so those are types of forces. Now, what's interesting is any force here that we listed, I'm going to put number 1 up here, all have the same units. And all of these have units of newtons, okay? Every one of them. Even though they're, the explanation of the force, the explanation of the push or pull is a little bit different. All right, now to understand newtons, I'll just put the equation here, F equals ma, because this is an equation we're been exposed to with Newton's second law. I've left the sum sign out here because I'm only going to deal with a single force here. Units for mass are kilograms. Units for acceleration are meters per second squared. So collectively, we would say kilogram meters per second squared, and we would refer to these as the base units of a Newton. And what this tells us is a force of 1 Newton will cause a mass of 1 kilogram to accelerate 1 meter per second squared. Okay, that's the base units of a Newton. Okay, now equations. Well, I have the one equation here that we're always going to be starting our kinetic analysis out with. F equals ma. We have all the forces acting on the object, and we get the product of mass times acceleration. When we start putting forces in on the left-hand side of the equality sign, we may be putting in different forces, like friction force. That equation is mu sub F, the coefficient of static friction, or sometimes we put S here for to emphasize the static, times the normal force. So, or mu sub S Fn. Now, if we're dealing with sliding is happening, then we would put in kinetic friction, and we would be mu sub K Fn. Okay, so this would just be kinetic friction or movement. But in essence, the same equation. Coefficient of friction times the normal force. For drag force, that's the other contact force we dealt with, 1/2 rho CdA V squared. Density of the fluid, coefficient of drag, which is a function of the shape of the object and the surface characteristics of the object, how well the fluid moves over the object. A is the frontal area being moved through the fluid, and V is the velocity of the fluid moving over the object. That whole equation still ends up with units of newtons, okay? And then the spring force is simply a coefficient times what I'll put in here, X, where X is the amount of compression or lengthening of the spring. And K is simply a coefficient of a spring constant. Sorry, a coefficient of the spring, or a spring constant is the way we would say that. That's just some number, and I'll explain this later on when we get to this force in detail. I put the negative sign here. What that means is that if I'm pulling a rubber band apart, it wants to create a force back in. If I'm pushing a spring together, it wants to push back out. So there's always an opposite reaction, direction of the spring force based upon whatever is causing that compression. Okay, so those are different equations of force. And then let's see, last thing I want to tell you about is force is a vector. And remember, vector math is different than scalar math, and therefore it's represented by magnitude and direction. And these are important to consider when we start doing our kinetic analyses. And in general, I'll just do an arrow here representing a force vector graphically, where the length of that arrow represents the magnitude. Obviously, this represents the direction. And then there's two other points that we need to, two other phrases that we need to understand. Point of application, that's where the force is being applied to the object. If it's a contact force, we can draw the point of application on the object. If it's a non-contact force, we draw the force acting at the center of mass of the object. application. Boy, my writing's terrible. And then the other one is line of application. And this is just a straight line projection in both directions of the force vector. And that is helpful for when we start to do angular kinetics and we start looking at rotational forces like torques, moments, what have you. Okay, that's what I want to tell you about forces. I think I got it all here. Put a 2 there. Okay. So push or pull, that tends to call movement, types of forces, contact and non-contact, units, newtons for everything, and then some different equations. And there'll be specific videos on these forces as we go through the semester. Okay, thanks everybody.